Thank you. So today I'll be presenting my thesis entitled Surface Photomagnetism in Glass Doped with Cobalt. It's my second year of PhD student. In this presentation, I will be talking about the thesis objectives, sample preparation steps, show you some results, and introduce you to the future works that I will do. The major goal of my thesis is to investigate the magnetic switching photo-induced by a laser due to the cobalt transition embedded at the surface of the soda-lime glass matrix. Diffusing the cobalt into the glass results in the creation of cobalt oxides. Two types of cobalt oxides are present embedded at the surface of the soda-lime glass matrix. The first one in figure A is CO3O4 cobalt tetraoxide, and in the second figure B is the COO cobaltous oxide. Only the divalent CO2 plus ion carry a magnetic moment. As presented in figure C, magnetic moment can be represented by a spin vector. It can be facing upward or downward. Spin ordering can be modified function of temperature. As an example, for antiferromagnetic material, as shown in figure D, this material show two magnetic states. Below a temperature called null temperature Tn, we can see an ordered state. This is antiferromagnetic behavior AFM. Above this temperature, the spin are not ordered, and this is called paramagnetic behavior PM. In the literature, in the case of bulk cobalt oxides, both cobalt oxides are antiferromagnetic, but each one of them has its different null temperature, as depicted in figure E. And we can recall our objective, which is to switch between both cobalt oxide using a laser, resulting in a drastic change in the magnetic material behavior. Four main steps are needed to prepare our materials. The first one is cobalt deposition, then the cobalt diffusion. The third step is dedicated to creation of the nanoparticles, but I will not talk about this in this presentation. And as we go, we should always characterize our samples. We will start by the cobalt deposition. We deposited our cobalt using DC sputtering. In order to diffuse it, we will use the thermal pooling method, where FASI, field-assisted solid-state ion exchange, is the physical phenomena involved responsible of the cobalt diffusion. For this reason, a thin film of 60 nanometer of cobalt was deposited at the surface of the soda-lime glass, then introduced into an oven having a temperature of 400 degrees. And simultaneously, we apply an external potential difference of 400 volts. This potential difference will induce an electric field, and this electric field will diffuse the sodium cation into the direction of the cathode, resulting in a depletion region where the cobalt will diffuse in order to fulfill the empty volume. Due to the ion exchange, an electric current is measured to track the progress of the process. We can observe visually the difference between colors before and after thermal pooling. We are working on optimizing the first two steps, and we are using different characterization technique. The first one is absorption spectroscopy, where we took glass as a reference of the measurements. Tests are performed on the samples before and after thermal pooling. The measurement can be plotted as absorbance function of wavelengths. As we can see, no absorption peaks were observed in the case of cobalt thin film. On the other hand, for the diffused cobalt, we can see 3 absorption peaks. Top plot was calculated and plotted using absorbance data. The goal is to estimate the optical gap of the examined material. For cobalt thin film, it presented a null energy band gap value confirming its metallic behavior. On the other hand, after thermal pooling, the diffused cobalt showed 3 energy gaps that correspond to the value found in the literature. These 3 energy gaps represent cobalt tetraoxide CO3O4. Thus, the diffusion of cobalt was done successfully. Another method is Raman spectroscopy. The Raman setup used in the characterization has a wavelength of 633 nanometer, maximum power density of 10 milliwatt, and a diameter of 2 micrometer. The goal is to insulate a material with the laser, then collect and analyze the scattered light resulting from this insulation. So a Raman shift function of intensity graph is the result of such a measurement. Starting by measuring the cobalt thin film at the surface of the glass, we can see no spectra at low power densities. This confirms another time the metallic behavior of this layer. If we increase the power density to the maximum, the cobaltous oxide COO signature is measured in addition to a scar at the surface of the treated area, and this is due to thermal heating. If we stop the experiment and we redo the measurement at the same treated area for low power densities, the signature of CO3O4 appears confirmed by 5 distinguished peaks. Another method to confirm this is to compare it with the red spectra of COO, where we can see the presence of a upshift and as well as the appearance of a peak at 624 centimeter minus 1, confirming another time that this is CO3O4 cobalt tetraoxide. And increasing the power density will induce the switch between the cobalt oxides at high power densities. If we measure the sample after thermal bonding, we can see the two types of cobalt oxide that can be reversed a function of the applied power density. This confirms so far the a part of the main goal of my thesis, which is to switch between those cobalt oxide using a laser. And to complete this investigation, magnetic properties should be measured for these cobalt oxides. In order to do that, to measure the magnetic behavior of these samples, we will use SQUID, superconducting quantum interference device. Using this machine is challenging because we should cut a 5 by 5 centimeter sample into a small one to fit it inside a straw having a diameter of 5 millimeter. It requires a precise cutting procedure to avoid the cracking of glass, or even worse, by producing some impurities. So the setup worked by generating an external magnetic field to measure the magnetization of the sample at any chosen temperature. Despite the challenges, some measurements were collected. For example, in figure A, we can clearly see that the glass behavior in the graph of magnetization versus field graph confirming that the glass is diamagnetic, has diamagnetic properties. Then we measure in figure B the glass covered with cobalt, and we can observe a ferromagnetic hysteresis loop that saturates above 20,000 Oersted, confirming that this cobalt is metallic, and in the literature we know that the cobalt is ferromagnetic. So, and as well, we can see the signature of glass, which is diamagnetic, and we remove it in figure C, and we can see clearly the ferromagnetic behavior of cobalt. We are now in the phase of investigating the cobalt oxide using the SQUID, so we hope to show you some results soon. For future works, I will be optimizing the parameters of sputtering machine and the thermal bonding accordingly. And I will, of course, do some trials using SQUID by adding the laser to see the transition between cobalt oxides. And that's it. Thank you. I'll be glad to hear your questions.